Hello, everyone. We are doing chapter 2, and that's over motion in one dimension. Guys, mostly in this chapter, I'm going to introduce you to kinematics towards the end of the chapter, but we have to go over really basic, I think, kind of physics stuff that you have already learned about in previous, like middle school time, and then maybe just take it a little step further, but not too much. So chapter 2 is about position, motion diagramming, or displacement, distance, velocity, acceleration. So I'm going to go through like half of these slides pretty quickly, and I'm doing that because I think a lot of this stuff is just common sense. And that will give us then, for my plan on Monday, when you come in on Monday, we are picking up right where we left off here. I want to finish up, or I at least want to get to what these kinematics are, and then I want to talk about, too, the relationship between position, velocity, and acceleration, and specifically how that relates with calculus. So, if you didn't watch my favorite dude that you watched in the video for homework last night, then please make sure that you watch that over the weekend and that you take very good notes on it, because we're going to discuss how we get velocity from position. How do I get acceleration from velocity? And then the relationship between them. Okay. I also, just as a reminder, posted the question on how to do and finish number 17 from your test as a separate video, because if you want to watch that, that's totally up to you, but you don't have to watch it, okay? So, our goal in this chapter is to understand what kinematics are. Kinematics is really just a way that we can describe motion without describing necessarily the forces that are going along with it. It's just the motion of particularly an object's position, or the motion of its velocity, or the motion of its acceleration. And a lot of times you'll see that kinematics are going to deal with maybe two of those three things. So maybe I know what a velocity is and I know what an acceleration is, and then from those things I could find a displacement. Or maybe I was given displacement and acceleration, and from that I can find a velocity. So kinematics is just ignoring all of the outside forces that may have caused a change in motion. We're just actually looking at the motion of a particular object. And in this chapter, we're focusing on it in one dimension. Guys, chapter 4 is the exact same thing. The only difference is we'll do it in 2 dimensions or in 3 dimensions. So that's the only difference between the chapters. There's a few different types of motion. Translational motion is probably what we will focus on the most, and that's translational motion is just a straight line path. So an example would be a car traveling on a highway. As long as you're moving in some straight or linear fashion, we have translational motion. Rotational motion is where we have some type of rotation. And so an example of that could be Earth's spin on its axis. And then there's vibrational. Vibrational, we're really not going to get into until the very last chapter in this year, which is going to be oscillations, because that's going to be an example of the back and forth movement of a pendulum. We had thought a lot about vibrational last year in AP Chem when we thought about like solids, because you know that they have some type of vibrational movement. Liquids have vibrational, rotational, translational, all of those things, because they can rotate around, they're going to vibrate still, the atom itself can vibrate in its place, and then they also move in straight line paths, so they have translational motion as well. So you've seen all of these, you've heard all of these, but now we kind of have to think about it on a macroscopic scale instead of so much a microscopic scale like we did in AP Chem. Physicists love particle models, or what we can call a motion diagram. Motion diagrams are ultimately just showing what's happening in the motion of a particular object. If you use a motion diagram, you are going to draw the picture. You're actually drawing the object itself. A type of motion diagram is a particle model. And a particle model is, instead of actually drawing the object, I'm just going to represent it as a dot, as a particle. Easy enough. So, for example, let's say that I have a rocket launch. If I look right here, so if you're looking at part A, this is just your rocket launch, you know that a rocket is going to accelerate as it leaves from the ground. So I have to represent that somehow in acceleration or showing that kind of motion. If I want to do that, and I think it's really hard to see those guys, so let me actually make them bigger on the Prometheus board. Okay, so if I had a rocket launch, I'll just make this my starting point, and let's just call this position 1. So I'm going to call it R1. I'm just letting R be the position of the rocket in its first position, so at the origin. Then I know that it's going to move up a little bit, so I'm going to call that R2. But then again, I have all of these exhaust fumes that are coming out of the rocket that are pushing, so the thrust is pushing it up, so I know that it has to be accelerating, so I'm going to make the next position be a larger space than the first position because I'm trying to show that it's accelerating. And then let's say we do 4 of them, so I have 4 particles. So I have this one, R4 should have an even larger space between that one and R3. Again, I'm trying to show that it's accelerating. So I can see that the space in between the particles is just representing if something's accelerating, if something's staying constant, but then I could connect all of these to show that overall the path of motion is just upward. Okay, another one that they have on your slide is a car stopping. So when a car is stopping, then I know that it may be going quickly at first. Like, let's say that you didn't see a stop sign, so you slam on your brakes. So at first I may be traveling pretty quickly, so let's call that R1. This is R2, but now I have to stop suddenly. So what I'm showing is, ultimately my direction is going this way, but I'm seeing that I'm going from a larger space to a smaller space to an even smaller space. So I must be decelerating somehow. And this would be an example of what we could do then for a car stopping or slamming on your brakes. So we can show the motion just by using particles, and you may see quite a bit of these on your AP test just because it's a really easy, nice, fast way to represent a motion of an object. We also, though, can represent or trace the actual path of the object, and so what we will find when we get into chapter 4, if we throw a ball at a specific angle, and I know ultimately, and you'll learn ultimately, it will have a trajectory. And we'll find out that that trajectory is going to be parabolic. But I can say, here's R1, here's R2, here's R3, here's R4, here's R5. So sometimes the actual motion itself will kind of lead to, sometimes the motion diagram itself will lead to the actual trajectory or path that the object took, which is why there's one that says accelerating, a car accelerating up a hill. And so on that one, it actually has it at some type of incline, how it's getting faster. I don't need to have it, though, showing on an incline, because I can say that the motion diagram is ultimately this, I'm accelerating, and then I would just have to specify that it's on an incline. So I don't necessarily have to show the exact path that the motion is going on in terms of how the object is actually moving. I just have to show in a motion diagram, is it accelerating? Is the velocity constant? Is the position constant? And if that's true, then the position, you're just going to have one dot, okay? So that's a motion diagram. And we, again, will use particle diagrams because they're just easier, and I can't draw, so that's pretty much why we have to do particle diagrams. Okay, let's keep going. Position. The object's position is its location with respect to a chosen reference point. I don't care where you place your origin, just as long as when you math, from this point on, wherever you take your origin or wherever you set your origin, make sure that your math is right. So if I look here at point A, I have the car moves to the right between positions A and B. And I set my origin just right here in the middle, no big deal. Okay, on this one, it says the car moves to the left between positions C and F. Okay, so the car is moving this way between positions C and F. So they probably made C their reference point and then followed what the car's motion was between here and then F. So I don't necessarily have to start my origin at 0. I don't have to, but you can start your origin at 0. It doesn't really matter. For us and in kinematics, we're not going to deal with anything rotational for a while. We won't deal with anything rotational at least until chapter 6 when we talk about circular motion in terms of Newton's laws with forces. So until we get there, my goal right now is to just talk about translational motion. And I think that's going to be a majority of your test anyway, is translational motion. So for this, all I care about is representing translational motion. And then, of course, I can have a chart plotting position with time and then specifically positions on here. But I have times and then specific positions. So if, let's say that I have this data, and this is table 2.1 in your book, and I want to graph it. So I want to have a PT, or a position time graph, that shows the motion of the particle. Anytime you draw a PT graph, I would like you to always have a curve, or some, not necessarily a curve, it could be a straight line too. But I want you to somehow connect all of those position points, those data points that you graph. You should always connect them, okay? Always, always, always. And that's true on your AP test as well. So this position time graph is just showing the motion of the car, specifically just from this example here, okay? So I can see that it has some type of curve to it. And if I see that it has some type of curve, then that's telling me that the velocity must have not been consistent or constant throughout the whole thing. So let's compare what position time graphs may look like if we're talking about something that has constant velocity or constant speed versus a graph that has increasing or decreasing speed. So on this particular motion diagram, I'm starting at time 0 and I have position 0 here. In 1 second, I move 10 meters. In 2 seconds, I move 20 meters. In 3 seconds, I move 30 meters. So every second, I am moving an additional 10 meters. Now that's, I mean, you can look at this and see that the spacing alone in between them is constant. So you know that this is a constant velocity, or constant speed. We should say constant speed. So when I graph this, I should get a nice straight linear line here. I should get a linear relationship. And I do. I see that here. So any type of position time graph that you see a nice linear line like this, then you know that speed is constant. So if you know this, speed is constant. Position versus time graph here. So my motion diagram is telling me I'm starting off at 0 seconds at 0 meters. In 1 second, I go 2 meters. In 2 seconds, I go 8 meters. In 3 seconds, I go 18. 4 seconds, 32. This is not some type of even interval. So because it's not an even interval, I'm not going to get this nice linear relationship between position and time like I did when speed was constant. This is telling me then that speed must be increasing. And you can see that, guys, too. I mean, this graph should make sense then logically with a motion diagram. If I have increased intervals, that means I'm speeding up. So that means my graph should not be a linear relationship like this. I should have some type of curve to that graph, and that's what we see. So some different position time graphs that you may see as well. If you're looking at, actually, you know what? Tell me on homework for Monday, or not tell me, but for your homework on Monday, I want you to go through and tell me what's happening in each of these graphs. So is speed in this position time graph, is it constant? Is it increasing? Is it decreasing? Is it positive? If I think about it in velocity, would the velocity be positive? Would the velocity be negative? Tell me what you think each of these graphs are, and then Monday we'll talk about it. Okay, displacement. Displacement is just defined as the change in position during some time interval. So we represent displacement as delta x. You may also see it as delta D. So you'll see displacement as either X, or you may see it as Y, you may see it as D. I don't care what you write, just as long as you're consistent in your variables throughout your entire problem. So if I designate displacement in one of my equations to be X, then make sure that as you're continuing to do the math on that, you leave it as X, don't change it as like D, okay? So we're going to represent this as delta X or delta D or delta Y, whatever we're doing. And guys, ultimately, that just means it's final minus initial, because delta is just change in. So I'm going to take whatever position I ended with and subtract it from whatever position I began. Our units for displacement are meters. Displacement is a vector, so it could be positive or negative. It just depends on the direction. So let's say that I start right here, between this 4 meters and this 2 meters down here in the bottom corner. And then let's say I go all the way around my rectangle and I end up right back where I started. Ultimately then, I know that my displacement would be 0, because if I end where I began, the displacement has to be 0. But is distance equal to 0? No, because distance is a scalar and distance is dependent on the path. Displacement is not dependent on path. All that displacement cares about is where I ended and where I started, and then the direction. And distance just cares about what's the actual path that I took to get there. Okay, so again, this is just another example between distance versus displacement. Assume a player moves from one end of the court to the other and back. Distance is twice the length of the court, and distance is a scalar, so remember that distance is always just going to be positive. All scalars, I'm never going to add a positive or negative in front of them because it's just a scalar. There's no direction that's associated with it. But the displacement, if I start from one end of the court, go to the other end, and then come back from where I started, displacement is 0 because I ended where I started. So final is equal to initial, easy enough. We've already talked about this. A vector quantity is magnitude and direction. A scalar quantity is simply just magnitude. So for vectors, we need to indicate direction by using a positive or a negative sign in front of the magnitude, and that will tell us the direction. Average velocity. There's 2 different kinds of velocity that we're going to talk about. There's average velocity, and then there's instantaneous velocity. We will probably deal more with average velocity than we will be dealing with instantaneous velocity. So average velocity is the rate at which displacement occurs. So velocity is dependent on displacement. Velocity is dependent on displacement. But speed, average speed, is dependent on distance. Guys, this should make sense because displacement is a vector and velocity is a vector. So if velocity is dependent on displacement, those two are vector quantities, then that means that average speed, which speed is a scalar, it's not dependent on direction, it should make sense then that speed is going to be dependent on distance, which is another scalar, okay? And all of those things are just rates, which means that time, the time interval is also important. So for average velocity, we're going to take our change in displacement, our change in x, so final minus initial, over our change in time. X is just indicating that it's the motion along the x-axis. So when we get to the point where we have 2 dimensions that we'll focus on, then those are going to be 2 different types of average velocities that we have to account for. So I'll actually do this twice if I have 2 different dimensions. Versus if I have 3 dimensions, I'm going to do it 3 times. Versus if I have 1, we'll just do 1 calculation. The dimensions for average velocity is just length over time. And the SI units are going to be meters per second. So all of our average velocity should always be in meters per second. I can find average velocity from a position time graph because the slope of the line of a position time graph is the average velocity, or is the velocity. Okay, we just said, for average speed, it is the same, it's a similar thing, it's just that for average speed, it's distance over time instead of displacement over time, because remember, speed's a scalar, distance is a scalar, so that's why we have to use the scalar quantities together. So neither average velocity nor average speed gives details about the actual trip described. We're just trying to find out more mathematical quantities instead of understanding what the actual trip was like. So the average speed is not the magnitude of the average velocity. A lot of people have a misconception that average speed is the magnitude of the average velocity, but that's not true every time. Sometimes it's true, but sometimes it's not. So I can't say that this is a true statement all the time. So for example, a runner ends at her starting point. So if I started one place, and then I go and go and go and go, and then I end right where I started, I know my displacement is 0. Therefore, if my displacement is 0, her velocity has to be 0 then as well, because velocity is just the displacement over time. And if displacement is 0, then velocity has to be 0. But you know she didn't travel a distance of 0, so that means that her average speed was not 0. So I can't say that the average speed is always the magnitude of the average velocity. That's not true. So it's important for us to know the average speed is not the magnitude of the average velocity in every case. Some cases you may see it, but not in every case. Okay, instantaneous velocity. Instantaneous velocity is about limits. I think you're doing that right now in calc. Yes? Okay. So the limit of the average velocity as the time interval becomes infinitesimally small or short, or as the time interval approaches 0. So this means that, let's see, here we go. Instantaneous velocity is just the slope of the line that's specifically tangent to what you're looking at with this, like let's say we have a position time curve. So if I have a position time curve, instantaneous velocity is just the slope of a tangent line, a line tangent to a particular spot on that curve, on your position time graph. So if we're thinking about it in terms of calculus, ultimately all I'm doing is I'm kind of dissecting it up so that way I can make it a limit. And if I think about all of these particular lines here, I can just think about, I can find instantaneous velocity by doing a slope of a line that's tangent. So if I was right here and I wanted to know, I'd be finding a tangent line here. Let's say that maybe right here I was at B, at this first B that you see circled. I want to find the slope of the line that's tangent. I want to find the tangent here to this one. Let's say I'm at this part of B. I'm going to find the slope of the line tangent to this one here. That's just to find instantaneous velocity. Guys, I don't think very often on your AP test I have ever seen you have to do instantaneous velocities. For the most part, you'll be doing average velocities. So as long as you can say, like you can represent how you would find instantaneous velocity on a graph. So if I give you a position time graph and I ask you to show me at B2, how would you find instantaneous velocity? And you could draw a line that's tangent to that particular point and say, this is where I could calculate instantaneous velocity. It would be the slope of that line. Then I think you would be good to go. Okay, guys, this is just saying slope has units. I mean, if you're at a position time graph and I have to find the slope, then ultimately it's going to be distance over time, which means it should be meters per second. So that should make sense. If the slope is velocity and velocity is measured in meters per second, the slope should probably have a unit. That's all I'm saying. Okay, so an instantaneous velocity in terms of an equation is for velocity, for instantaneous velocity, it's still my change in displacement, or my displacement over change in time, but it's as that time is approaching 0, so I'm thinking about the limit of it. So ultimately, velocity is the same thing as taking the derivative of position, which we will get into that beginning of class on Monday. So again, if you watched that video last night, then make sure you kind of look at your notes to make sure that you understand what the guy was talking about in the video, and then we're going to go through several examples of that too. Instantaneous velocity can be positive, negative, or zero. Again, that makes sense because velocity is a vector and it's dependent on direction. Instantaneous speed is just the magnitude of the instantaneous velocity, so it won't have a positive or negative associated with it because it doesn't have a direction. Vocab note. Velocity and speed usually indicate instantaneous value. So if I just say velocity, or if I just say speed, that means that it's at one particular moment in time. If we're talking about average velocity, or if you hear something about average speed, then I will use the word average in front of it. So you should always assume that any velocity or speed I give you is just an instantaneous one. Okay, guys, all of this stuff is just kind of talking about how we'll analyze a particular equation, or how we can analyze something that specifically is a particle under constant velocity. So it says constant velocity indicates that the instantaneous velocity at any instant during any time interval is the same as the average velocity during that time interval. So I can say that instantaneous velocity, which we just call v, is equal to my displacement, xf minus x sub I, over the change in time. So most frequently, we usually want to find a final position. Sometimes I can know the instantaneous speed that I'm moving, or the average velocity or instantaneous velocity. I usually know a time, and I usually know where I'm starting from, so I can find my final position just by rearranging all of this. And hopefully we should all know how to rearrange this by now, but just to be safe, let's just look at it really quick. Just be sure. You actually not assume. Okay, so let's say I have my instantaneous velocity is equal to change in x over change in t, which is really just the final position minus the initial position over time. So let me rewrite that. V equals xf minus x of I over delta t. Well, I want to rearrange this and solve this for final position, because that's maybe what I want. So if I want to do that, let's multiply v times delta t. That gives me x of f minus x of I. I just want x of f by itself, so I'm going to add x of I over here, so I can get x sub I plus v delta t equals your final position. Okay, so that's how you can derive it. I will ask you to derive certain things like this, but we're not at a point where we have to derive. Oh wait, here's your slides back up. We're not at a point where we can really derive any equation yet. Okay, so guys, we're going to stop here. We're going to stop here, which, guys, sweet, we made it to slide number 24. So we're going to start here on Monday. Make sure you watch, again, that video and understand those notes. If you have questions on this, let me know. Don't be surprised if you'll see something really exciting when you first come into class on Monday. Yeah, have a good weekend. Bye!